Log properties part 2. So these are the ones that are going to let us start solving problems and solving equations and things like that. So the first one that I'm going to do, I think we're at number 6 at this point. I can't remember exactly, but number 6 is referred to as the product rule. That doesn't look so good. Okay, the product rule. And so one of the things I want you to understand is just like other functions where we have f of x plus y, we don't write it as f of x plus f of y. That inside part is always sort of one thing. Just like we had sine of a plus b, we don't write that as sine of a plus sine of b. So in this case here, we actually have log of x plus y is definitely not equal to log of x plus log of y. All right, so we do want to figure out what a product rule looks like, and I just wanted to mention this little stuff right in here. So the product rule says this: what does log of a times b equal? And this could be any base. So remember that our base in here has to be greater than 0, and your base can't equal to 1. So what happens when we are multiplying inside of a logarithm? We can't just write this out as log a times log b. That doesn't work either, unfortunately. So what I'm going to do is I'm going to actually prove this one to you, because I want you to again see some of the processes that you can do when we're dealing with logs. I'm not going to ask you to reproduce this proof. So here we go. We get, I'm going to let m equal to log base x of a, and I'm going to let n equal to log base x of b. Now this is log form. If I change to exponent form in this case, exponent form, we ask ourselves what's the base, and the base in this case is x. What's the exponent? Logs are exponents, logs equal exponents, and then a is the leftover number. Just like in the other one, my base is x, logs equal exponents, logs are exponents, x to the power of n is equal to b. So the reason why I'm doing that is because if I wanted to figure out what log base x of a times b is equal to, I'm going to start off by just figuring out what a times b is equal to. And if I look up here, I've got a right here and I've got b right here. So a times b is going to be x to the power of m times x to the power of n. Using our exponent laws, remembering logs are exponents, we get x to the power of m plus n. When we're multiplying, we add our exponents. So now to figure out what log base x in front looks like, I'm going to log both sides. And I'm going to use base x for this one. So log base x of a times b is equal to log base x of x to the power of m plus n. And this is where we're going to use some of our log properties. So log base x of a times b is equal to this. Now remember, yesterday we found a log property that said log base a of a to the something is equal to the something. So log base x of x to the something is equal to the something. Well, look up to what we started off with. We started off with these two things. We started off with m and we started off with n. So that tells me that log base x, any base, a times b, is equal to m, which was log base x of a, plus n, which was log base x of b. So what's happening is that when we are multiplying inside of a logarithm, we actually add the logarithms. And if you sort of think that this is similar to something you've heard before, it's because of this property right here, right? When we are multiplying our powers, we actually add our powers. Logs are exponents, and they work very similarly as we go through the properties. Now that leads us to 7, which I don't think I'm going to need to prove because 7 is very similar to 6. And 7 is called the quotient rule for logs. Quotient means divide. And the quotient rule says that we want to figure out what happens with log base x of a over b. Well, if we think about this, logs are exponents idea. If you realize that when we're multiplying inside of our logarithms, we add our exponents, right? What we think of as an exponent. So that means that when we divide, we are going to subtract our exponents. So log base x of a, starting with the top, minus log base x of b. Excuse me. So this is our quotient rule. One of the things that we can do with these rules is I'll just show you a quick example. We can combine the logarithms to write as a single logarithm. And so what I mean by that is that we've got log of a plus log of b, maybe plus log of c. As soon as we see these plus signs in between logarithms, you have to think, okay, logs are exponents. When I'm adding exponents, what am I really doing? Well, I am multiplying. So I'm going to go a times b times c on the inside. Notice that the base for all of these things has to be the same, and in this case, it's base 10. For the second one, I'm going to go log of a minus log of b plus log of c. I'm going to use base 10 again. For this one, what's happening is that there's going to be some division in here. So this is, we go log of a, and if you think about it, it's a divided by b and then times c with a log in front of it. Or if you think about order of operations, this is going to be a divided by b and then times c, and so your c is on the top. Now, the other thing that might happen is that if you don't really see that, the other way you could think about it is that you could rearrange it. Since we're just adding these logs, I could add the positive ones together and then subtract the bottom one. And this one would be my multiplication, and this one would be my division. And in either case, you're going to get that b into the denominator. Keep in mind that you do want to make sure that you have the same base. So maybe instead of just writing log base 10, I'd write natural log. That could work. And in this case here, for natural log, we've got a division and we've got another division. So we're going to have an a in the top divided by b and then divided by c, which means that the c is in the bottom. If you don't see that, another way of thinking about this is that you've got the natural log of a minus, factor out that negative, natural log of b plus natural log of c. That means that these guys are being multiplied in the bottom because this is your division sign right here. Okay, so here we go with the last rule. Now, if you've done some math school before, some Kumon or anything like that, you might have actually learned some of these log properties, and there can be like tons and tons and tons of them. But I'm only going with 8 because we can develop anything else we need with these basic sort of 8 things. The last one that we're going to need, and it's a fairly important one, is something called the power rule. And what we want to do is we want to figure out what happens when we have log base x of a to the power of something. Now we know this. We've already learned that log base a of a to the x, well, out pops the exponents because logs are exponents. But what we want to do is figure out what happens when the bases don't match. So in this case, the bases match. In this case, the bases don't match. So again, I'm going to start off with a little bit of a proof so you can see how this goes. I'm going to let n equal to log base a of x, or sorry, log base x of a. If I change it to exponential form, x to the power of n is equal to a. So we start off, if I'm going to try to figure out what log base x of a to the power of b is equal to, I'm going to start off with what a is equal to. Just build it right from the middle part here. I'm going to start with the a part in here. So a is equal to x to the n. That's where I get this guy from. Now what I need to be able to do then is I need a to the power of b now. So what I'm going to do is I'm going to raise both sides to the power of b, x to the n to the power of b. Remember again that logs are exponents, so think about what you're doing with your exponents. When you have an inside and an outside exponent like this, we multiply them. So we're going to get n times b or b times n. Inside, outside exponents, we multiply. I'm going to log base x both sides. And then I have this property where the bases match on this side. So if the bases match, logs are exponents. Out pops the exponent, which is b times n. Now, how did that help me? Well, right at the very beginning of this, I let n equal something. That's what my n value is going to be right there. So I get the fact that if you have log base x of a to the power of b, the b pops out, and inside you're left with log base x to the power of a. So this is like having your inside and your outside exponents. So inside, outside exponents, we multiply our inside and our outside exponents. This is this is that same log property that we did when we did our exponent property right here. It is very strange looking. So this one, let me just write it out again. Log base x of a to the power of b brings that b down in front times log base x of a. So what this tells us is it tells us that if I had log of, for example, a squared, another way of writing it is 2 times log of a. Or if I had 1/3 log of a, I could also write this as log of a to the power of 1/3, or even log of the cube root of a. So this is how we can use this idea. So that coefficient in front of the logarithm is actually an exponent. Okay, couple of examples. Let's do one more. Write as a single logarithm. Here's the first one. 2 log of a minus 3 log of b plus 1/2 log of c. Remember, overriding all math is order of operations or BEDMAS. There are no brackets here, but there are definitely exponents. Those exponents are kind of hidden in our logarithms, but our exponents are sitting right here and right here and right here. So the first thing that you want to do is you want to work with those exponents and bring them up so that you have just logs here. And so we've got 1/2, or so log c to the power of 1/2. Then we ask ourselves, is there any division multiplication? And the answer is definitely yes. Division multiplication are right here and right here. It doesn't look like it, but remember we're dealing with logarithms here. In fact, there is no addition subtraction of logarithms. We are multiplying and dividing. So when we want to bring this all together, my log is base 10. I've got an a squared divided by a b cubed multiplied by a c to the 1/2. Or, if you want, we could have an a squared times the square root of c divided by b cubed. And either way is acceptable as we go through. Now I'll show you a trickier one. Let's say we have 5 log base 3 of a plus 3 log base 3 of b minus 2. So we want to write this as a single logarithm. The bases must match. So really, the problem that we're having right here is this guy. This guy is a problem because if I want to write this thing as a single logarithm, I actually have to write that as a log. So we've got 5 log base 3 of a plus 3 log base 3 of b. And this has to be log base 3 of something. We have to write it as log base 3 of something. So if you think about this over on the side, 2 has to be log base 3 of something. Now, if you can think of that something in your mind, fantastic. If you can't, you can change this to exponential form. The base is 3. Logs are exponents. 2. Left over is that little square that we've got. So 5 log base 3 of A, and then 3 log base 3 of B, minus log base 3 of the little square that we've got here, which turns out to be 3 squared, which is 9. Now double check. Log base 3 of 9 has to be something you can evaluate. Log base 3 of 3 squared is 2. Oh, it works out just fine. Now we start dealing with our BEDMAS stuff. Maybe you've done that already. My exponents need to be dealt with. So I've got log base 3 of A to the 5th, and then log base 3 of B cubed minus log base 3 of 9. And then I deal with my division multiplication. So I've got log base 3 of A to the 5th times B cubed divided by 9. And that's going to be what your answer looks like. So that's how you can incorporate numbers and stuff into it. Okay, so last example before you guys are going to try some on your own. These are my personal opinion, the trickiest type of questions. So I'm going to give you that log of 3 is equal to x, and log of, log of 4 is equal to y. Notice that the base is 10. What you want to do is you want to find an expression for each of the following. And your expression can have x's or y's and numbers and all that kind of stuff into it. So the first thing that I'm going to do is we're going to find an expression for log of 9. So when you think about log of 9, what you want to do is you want to look at the given numbers that you have. You have a 3, you have a 4, and your base is 10. And is there something in there that you can actually write with 9? Well, we know that 3 squared is equal to 9. So if I wanted to find log of 9, I could write it as log of 9 is log of 3 squared. Using our exponent rule, remember that the exponent can actually be brought down in front of 2 times log of 3. So in the previous question, we wanted to bring it up so that we could incorporate it. In this one, we don't want it, so we want to bring it outside. We are given that log of 3 is equal to x. So that means that this expression is going to be 2 times this guy, which is x. So that means that log of 9 would be 2x. So we're just finding an expression for this. If I wanted to find an expression for log of 2, again, we want to figure out how we can combine 2 with a 3 and a 4 and a 10. Well, 3 has nothing to do with it. 10 has nothing to do with it. I can get a 2 out of 4, though. So we know this. We know that log of 4 is equal to y. Log of 2 squared, we got to get that 2 out of there, is equal to y. Bring the 2 in front. 2 log 2 is equal to y. To get the log 2 by itself, divide both sides by 2, and we're going to get log 2 is equal to y over 2. You've got yourself an expression for this. Okay, so now let's talk about log of 6. So log of 6, we have to think about, again, can we get something to do with 3 and 4 and 10? And the thing is, you can actually also use 9, now that you figured out 9, and you could use 2 as well. So the numbers that we have are 3 and 4 and 10 and 9 and 2. Is there any combination of those things that we could use to find 6? Hopefully you can see it. Log of 6 is equal to log of 2 times 3. So I'm going to use this guy and I'm going to use this guy. So that's going to equal log of 2 plus log of 3. We can split up those logarithms. We just figured out that log of 2 was y over 2, and we were given that log of 3 was equal to x. And so your expression would be y over 2 plus x. Okay. So the next one that I'm going to do is I'm going to do log of 9, let's do 27 over 100. So keep in mind, again, that the numbers that we're working with so far are 3, 4, 10, 9, 2, and now also 6. We've got all those numbers that we have expressions for already that we can work with. Well, let me think. 27 is 3 times 9. We could do that. Or you could go 3 cubed. So this has to do with the 3's for sure. 100 doesn't really work with anything except for the 10. So let's deal with this logarithm. And I'm going to write these as powers of those base things. So this is 3 cubed on the top, and this is 10 squared on the bottom. So we're going to end up with log of 3 cubed minus log of 10 squared. Remember, those exponents, we really don't want them there, right? We only know stuff about 3 and 10, so get rid of them by putting them in the front. 3 log 3 and 2 log 10. Log 3 was given to us as an x. Log 10 is not given to us, but our base is 10. It's a common logarithm. So log base 10 of 10 is equal to 1. The exponent pops out, so this is going to be just 2 times 1. So our expression would be 3x minus 2. These laws, these types of questions take a lot of sort of playing around. But the idea is here, taking a look at this, what base numbers do you have and how can I combine them to make these values? Okay, go and try some questions and good luck.